All right, so now I will play myself. That's my other role. I'm in a sort of a double role as organizer and speaker, which is a little bit unusual. And that seems to be caused by the fact that I'm turning older this semester, and it's also going to be celebrated on the boat later this week. Yeah, so what I want to say about, I should maybe start by apologizing to the organizers for not supplying an abstract. And the title, I think, is just the title of the semester, Arithmetic Statistics. And I somehow felt, since I'm now in charge of organizing a whole semester on arithmetic statistics, I typically get these questions: what is arithmetic statistics anyway? Is this something new, or are you now a statistician? And in particular, I'm from Leiden, where we have statisticians, and they are different from other mathematicians. So then they ask, where are you actually? And being a statistician, that's not the point here. Some people say maybe it's probability theory. And the question, what is new here? And this is a non-mathematical question: is this something new? And that means that the answer can be either yes or no, depending on your point of view, and it's perfectly reasonable. So why isn't it new? Let me start by that. Because the questions that you ask in arithmetic statistics are about average behavior, about the distribution of possible outcomes of whatever questions you're asking. And these questions are perfectly natural, and as long as mathematics has been around, if a question just has an answer yes or no, then the next question is, how likely is it to be yes or no? What is the more frequent one? So these questions are as old as the world. So there is nothing new under the sun here. On the other hand, if you sort of look back a little bit, and if you get older, that's what you tend to do, right? Then you could say that certain things did change a little bit over the last few decades. So why do we now talk about arithmetic statistics more than we did, say, 40 or 50 years ago? What were the things that influenced these? And I think that if I look back at my decades in mathematics, then the thing that changed when I was a student is that machine computations, computer calculations, became part of mainstream mathematics. In the old days, people like Lamer, who did to do factoring with mechanical devices, that used to be sort of a little bit out of the mainstream. But if you think, so the computations, that is, I think, starting from the 1960s. And you can wonder whether something like Birch, Swinnerton, and Dyer would ever have been discovered if it just had to be done by hand calculations. Yeah, Birch and Swinnerton and Dyer actually used computer calculation to sort of look at these things. And in those days, also, mainstream mathematicians started using or developing actual computer algebra programs. So in the 1970s and later, I think people like Henri Cohen and others, 70s, 80s, there was computer algebra systems came up. Paris is from the 80s, 90s, I don't know, 80s, right? Yeah, there was Magma, Paris, and these became sort of mainstream. So nowadays, all mathematicians from day one actually in number theory know how to use these systems, which means that you can do calculations that in the old days were, more or less impossible. And it doesn't mean that everybody now is a computer scientist and does coding. Also, this is the beginning of algorithmic number theory. Of course, there have been algorithms in number theory. They've always been there in number theory. But it also became a branch of mathematics, which is a little bit bordering computer science in the sense that if you have a method to do something, having an algorithm, you should typically you would also add that your algorithm was, say, polynomial time, or add a runtime calculation, sort of provided with the data. In the old days, for instance, factorization before RSA was not a problem, since there was an algorithm, period. You can just trial division solves it. But you discover then that in real life you cannot factor because the algorithm is way too slow. So RSA, that also is the link with crypto. This was the time when every number theorist who thought of a grand proposal started saying that he did actually crypto, and that is still somewhat the case. And in a way that is true because all these algorithms in crypto typically use primitives from number theory. And that also changed the point of view on number theory quite a bit. And this is also when things like ANDs were created, and these things still exist. And the final thing, this is all long ago, 20th century, I think the most recent change that we have is the availability of online data. So there is now data storage which is online. And the most prominent example in this area, I think, is the LMFDB, I think. So that is the L functions in modular form database, where you can really find all the objects in number theory or in algebraic number theory, like number fields, elliptic curves, Abelian varieties, their L series. There is massive data that you can now easily access online, and you can try and find regularities, irregularities, and randomness. So the aim, so to speak, of this whole statistics business is find regularities and randomness. So typically what you try and do, if you study something, you prove theorems. As a mathematician, you say it has to be, these are the structural constraints. And then you think, well, if you found everything, all the rest that's left is randomness. And not just you want to find it, and that is maybe the hardest thing, prove it. So if it's a yes-no question, and it's you think it should be 50-50, completely random the answer, yes or no, first of all, make mathematics. What do you mean by 50% of what? And then actually prove it. And that is quite a bit harder, because proving randomness, of course, sounds a bit weird. Now I'm almost getting philosophical on the morning at 9:20, 5 minutes into my talk. Proving randomness is something we can actually do. Last week we had in school, we have theorems that tell us, say that Frobenius elements are equidistributed over Galois groups or whatever. And these are actual theorems that allow you to show that certain behavior of the possible behaviors actually they occur in all the possible forms as often as they're supposed to. So at the end, we're still proving theorems, but the things we use into doing so has expanded, and all this has now been called arithmetic statistics. So we're not statisticians, not even probabilists maybe. We still do arithmetic, and well, this is so broad that you can easily have a semester of 6 months and having very many people doing very different things, and they all say, well, we actually fit into this. Okay, so this is sort of my general blah blah to start my talk, and to answer the question, what is arithmetic statistics? Okay, so that's our semester then, and to get to some more concrete examples, I was thinking, so what you should say, you don't just want to look back, so I want to present something that we don't know yet, conjectural a little bit later. Just show these by examples. As I said, we have theorems that actually talk about distributions, and distributions over what? So typically, if you talk about probabilities, the question is there a space on which we do this? What kind of space is it? Is it like a classical probability space having a measure, or is it typically something, say, a countable set that you need to give your own structure by ordering or whatever? And I think the randomness associated to that, I think that the example that I actually do need to talk about, because this is the occasion where both Henry Cohen and Hendrik Lenstra are in the audience, and the beginning, if you want, of arithmetic statistics for many people are the so-called Cohen-Lenstra heuristics. And they're still mostly unproved, so it's still sort of a guiding thing. As I said, heuristics, you can also call it a philosophy. I don't think Hendrik likes to be called a philosopher. But in a way, he's always right, since there are always statements that start with an if, namely, if something behaves randomly, this is the outcome. And that means that the outcome is something very precise that you can actually check. But it starts with if, and then what the randomness thing is. And that means that if you prove it, then he was right. And if you disprove it, he's also right, because it wasn't random, it was a theorem that someone missed. And that makes it almost a little bit religious. All people are always right. Well, why not? So what is the problem here? And this is also actually, it goes a little bit back to my own youth. I think it formally has been presented in the proceedings of the Journée Arithmétique, 1983. There is this famous paper, which is by Henri and Hendrik. This is the famous, let me also put where it was. Just this is an important country in the history of number theory. This was in Noordwijkerhout, which is in the dunes in the Netherlands. And this was the time, also Faltings came over for a day, for instance, because he had proved Mordell. All things happened. And there was a paper, and in those days, this is 40 years ago, so I also had a birthday in that year, and I was only 20. So I was just an undergrad, and these things happening in Noordwijkerhout. I had just become, I think, assistant of Hendrik in those days. He was in Amsterdam. I'm not going to tell you how old Hendrik is, but he was a full professor in the late 70s at some incredibly early age, I think, 28 or so. And there were people around him, like René Schoof, also in the audience. And these were the days when Hendrik was still wearing a leather coat and had a longish hair. It's hard to imagine, but these were really different times. Henri was a young guy. And these people got together discussing, in this case, imaginary quadratic class groups. So, and the question is, how do these behave? Imaginary quadratic class groups. Again, they're very classical. They've been defined by Gauss in terms of binary quadratic forms, so they have been around for since 1800, almost for 2 centuries already. But in those days, there were these Texas Instruments handheld calculating devices, and even though I've known Hendrik for 40 years, I've never seen him code or program anything, and he swears he never does it, and it probably is now correct, but it seems, the rumor has it, in the old days, when he was looking differently, he also had this Texas Instrument thing that had little strips. Oh, sorry. Sorry. Yeah, you say. As I said, it's before my time, but it seems that then, in the old days, in the basement in Amsterdam, Hendrik was there with his calculator, and he could feed it little strips. So the program had, don't know how many characters, very few, I guess. But if you efficiently used those, you could actually compute imaginary quadratic class groups in ranges where, by hand, it got already cumbersome, that Gauss maybe would have disliked already. There was also René Schoof as a young student, and he was the generation that actually had these huge piles of punch cards that you could bring to the basement of the university, to the computer science center, and you would give it to them, and then in the afternoon you could pick up your output, whatever it was. It might just said error, because there was a punch hole wrong, and then okay, you have to do it the day after again. But sometimes, of course, it was correct if things worked, and René actually got class groups of discriminants that he could see just once and look at it and throw it away, and nobody would ever find it again. Yeah, just for statistical reasons. If your favorite 20-digit discriminant, you've looked at it for a whole day, you throw it away, nobody's ever going to find that number again. So it's, yeah. And of course, what do you do with the output? You could say, okay, another group and another group. And the only theorem that you have about class groups, apart from the fact that with a discriminant, so you have a imaginary quadratic field, q square root whatever, d, where d is negative. And you know that the size of the class group, so we're looking at the class group of this number field, and its size tends to infinity with the discriminant, not effectively, but like square root d, so they get larger and larger, and you really get interesting groups. And you can ask many questions about them. And the discovery, if you want, of Cohen and Lenstra is that if you stay away from theorems, as you always do, because then it doesn't apply, so Gauss proved something about the two-part, I will get to that in a moment, in a slightly different context. If you take the odd part, then, so outside 2, for which you have theorems that prevent it from being random, is a random abelian group. That is sort of the one-line summary. Which of course is very vague, as it goes with philosophies or principles. And this means something in practice. And I don't remember if there ever was a talk in Noordwijkerhout. I think I only was there one day on bike with V. Bosma, who later went to do magma. We were just young guys and looked at all these weird mathematicians. And now we're part of the weird scene. And did you give a talk on this actually, Henri? Yeah, there was a talk. Okay, maybe on the day I wasn't there. Anyway, I don't remember it. But this was maybe the summary of the talk. And what does that mean? And later, I think I asked Hendrik, why does random mean weigh things by the order of the homomorphism group? And then he told me that Henri once entered his office with the question, what's the reason why if you take, you don't look at, say, the 3 part, if you know that the 3 part of their class group, so we're in the situation there, it's a magic array class group, suppose it has order 9. Then you know that if the group, there's 2 possibilities. It is either cyclic, z mod 9z, or it is non-cyclic, 3 times 3. And you can just count how often the first thing or the second thing happens, and the question was, why is the cyclic case so much more frequent? And actually, if you have lots of data, you easily discover that this doesn't happen half of the time, it only happens 1 out of 9 times, which means that the other fraction apparently is 8 over 9. And you think, well, must be the class number 9, and maybe if you make it 5 times 5, it becomes 1 over 25. But Hendrik said, no, that's obvious, since if you look at these groups, in this case, the automorphisms, the automorphism group of the cyclic group of order 9 is cyclic of order 6. It's z mod 9 z star if you want. And if you do the same thing for the 2-dimensional vector space over the field of 3 elements, then its automorphism group, if you know it like this, is the group GL2F3, which has order 48. And you see there's 8 times more automorphisms, and that's the reason why it's much less frequent. It differs by a factor 8. And the same factor 8 is what you find here. So the conclusion is that you should, the more automorphisms you have, the rarer it is for the group to appear. So you should weigh things apparently by 1 over the automorphism group. And in which way is that natural? And let me share the naturality of this feeling as Hendrik told it to me. Just imagine that you're creating the world. You feel yourself God as a mathematician if you want. And you create groups of order 9. Or in general, of order n maybe. Say billion, doesn't really matter. So you start with a set, V, a set of order n. And you're trying to figure out what a group is. You may not know yet, you can just start with compositions. So what you do is you look at maps from V to itself, star, which is a composition law. So for every 2 pairs you get a product, and you may get a group or not, and there's very many choices. If you count how many ways there is, you can just fill a multiplication table of this set, and for every of the n square entries, you can choose one of n elements. So it's n to the power n squared, it's huge. Usually you don't get a group. So under Darwinism, most multiplication tables are useless and disappear from life. You're left with the groups. So if V with star is a group, then you know there's only finally many choices for that group. Like here, there's 2 of them. And you can wonder for how many of these laws you get a group which is isomorphic to a given, if A is a group of order n, abelian or not, it doesn't really matter, I think. Say one of these 2, you can wonder how often it's going to be isomorphic to A. And now the counting is easy, because you just take your A and you map it to V, and you transpose the law, and you see how unique it is. There's n factorial of these maps. But then it depends on the number of automorphisms, how often it occurs. So what you find is this. So groups having many automorphisms arise only in few ways in this story, which means that the factor actually is what you should naturally expect. So this is the basis of the philosophy. And then, of course, as it happens, you want to make math out of this. So getting all these formulas in Henri's paper, then you should look, if you take a finite abelian, there are actually theorems by Philip Hall from those days, or maybe a little before already, that actually see that if you sum over isomorphism types, and you would use this factor, then you typically get nice expressions. And that's the beginning of the mathematical foundations of Cohen-Lenstra, if you want. It has gone a long way. We're now 40 years ahead, and there's many other situations. It has been expanded in various ways. I don't want to say too much about it. Actually, it's not my topic anyway, but given that all these people are here, I think I should say something about it. And if you want to know more, just ask them, they're all here. So making math, and of course you cannot do all finite abelian groups, then you just find that the probability for a given group to arise is 0, which is true but useless. So you typically take P groups, or groups that only have finitely many primes, S groups for finite sets, and you're in business. You also see that the distribution takes place on sort of rather discrete sets of objects. Yeah, here we only have two groups, for instance. And the example that I'd like to talk about a little bit more today is also a case where you don't have a probability space in any classical sense. Yeah, in number theory, you typically look at number fields or elliptic curves over the rationals, and these are countable sets. So your space typically is countable, and then the question is, what does it mean to have a density or a distribution or whatever? And the example I want to spend some time on, because it was sort of in the news lately, is the negative Pell equation that in the 90s I also looked at. So again, this is sort of old stuff. Negative Pell is the equation, if you do it without negative, it's the well-known Pell equation, which is to be solved in integers x, y, and z. And you can wonder, given your integer d, which is a positive integer, and many people don't like squares for the Pell equation if you want, then it's always solvable for every positive integer which is a non-square, and that's not due to Pell but to Euler, I think. Even though Lagrange maybe gave the first complete proof, it's always solvable. And it's just asking, if you want, about the fundamental unit. So this is directly related if you take epsilon d in q square root d, the fundamental unit. Then solving this equation is almost the same as finding the fundamental unit. The only slight difference is that this is in the ring z square root d, which may not be exactly the ring of integers. It's in principle, it's an order. But finding the fundamental unit is the same thing as solving the equation. And negative Pell, once you have units, you may as well wonder if the norm they can be +1, it can also be -1. And then the question is it still solvable? And that's not always the case. So you want to characterize the sets of integers for which this is going to be solvable. And that is not such an easy task. First of all, you need to find the d's that you want to look at all. So you see, let me call, let me go to the name, negative Pell, NPD, solvable. This is the set we want to characterize. And it lives inside a set that has some obvious conditions, S. Namely, if you take a d in S, a larger set S, if you take any positive integer, there's obvious reasons why you cannot solve this equation. If you take any prime dividing d, x squared minus 1 is -1 mod p has to be solvable. So you want only to consider integers without prime divisors. So if p is 3 mod 4, then p doesn't divide d. And also, you may as well assume that 4 doesn't divide d. Since modulo 4, you also cannot solve x squared is -1 mod 4. And this set is something that people have been looked at also in a different context. This is exactly the set of d's of the form x squared plus y squared, sum of integer squares with a GCD of x and y is equal to 1. So sums of coprime squares. Sorry? Yeah? As always, 40 years, Hendrik on first row, and if he sort of frowns, better be careful. This set, and you know exactly how many elements there are in there, so this set, if you count asymptotically how many elements are up to x, that is going to be x over square root log x, because essentially you use only primes 1 mod 4. And the constant is something that I think is 3 over 2 pi product over primes 1 mod 4. Oh, sorry for my 1 minus 1 over p square to the minus 1/2. So this is a well-known set. And the question that I want to deal with in this talk is, what is the natural density of S minus inside S? Which means that, that's the question. And this question was asked, you can, if you want, you can call it a conjecture. And it occurs in a paper by Nagel in German, in 1932. Namely, if you look at the fraction of D's for which negative PEL is solvable inside the set of S for which the sort of local conditions are satisfied, doesn't have a density. So does P, which is the limit, is there a PEL constant? This has obvious meaning, right? Elements in this set up to X for which negative PEL is solvable as a fraction of the full set exist. And is it actually something that is interesting in the sense that it is between 0 and 1? Maybe not the question is. And this question has been studied quite a bit, and in this form it is still open. You may know about a result, which is now a theorem, which is due to Peter Koymans, who is actually in the audience, and Carlo Pagano, which is very recent, 2022, I think. Namely, if you restrict to square 3D, so essentially to quadratic fields, then you may sort of order them by discriminant or by radicand. That doesn't make a difference for the outcome. There is maybe, if they call it P, so let me call this Q. They prove that if you define inside S the subset of square 3Ds, square 3, so essentially the real quadratic fields, and similarly there is the square 3Ds for which negative PEL is solvable, there is a natural density of sigma minus into sigma, in sigma. And what they do is that they confirm the conjecture that was 30 years old when they proved it. This exists, and it is 1 minus the product over a certain, over all G odd, which is something like 0.58057. Whoops. That is now a theorem. So this part of Nagel's conjecture has been proved. And I'd like to focus on the unproved part a little bit, which still remains to be proved, and I hope it won't take 30 years, but at least it doesn't hurt mentioning it already right now. And maybe Peter already is working on it, for all I know. So I want to add to this theorem the conjecture. Which already has been around for a while, and this conjecture says that Q also exists, and you can form it so Q exists and it's equal. Well, you can phrase it in various ways. Let me write it down correctly. So the idea is you start with the square free case, which you know what the density is, and then you sort of move from fundamental D to orders of index F. And for given F, you want to decide how likely it is that the thing is going to be solvable. So what do you get? The density, there is a P. That's because the fundamental case, then moving from the fundamental to the non-fundamental case, you're going to have all these F's. I'm going to show it in a moment. It's only about primes 1 modulo 4 P prime. This is the expected Euler constant. And then what you get to take care of the, if you want, the probability of the solvability in an order, you get something that looks a bit funny. It's a product also over the primes 1 mod 4. So maybe I should have actually joined it with that part, doesn't really matter. But this is sort of the easy part, it's about being square, and this here is where something happens. And the formula is as follows. Psi p over 1 minus p squared. Dot, dot. where psi is a function, of course, that needs to be defined, at least for primes p mod 4. So for p1 mod 4, this psi p has a funny expression, which I'd like to explain in the remainder of my talk. It is 2 plus p times 1 plus 2, 1 minus the order of 2 in p minus 1 over 2 plus p. Sorry, wrong, 2 times p plus 1. It looks so ugly that I always have problems remembering what it looks like. And the question is, why is this? So, first of all, let me say a few words about the theorem before going to the extension to non-fundamental discriminants. So the P, that is the part that comes from the sort of the theory of the class groups. So maybe, just for the context, the how much, 5 more minutes? Oh, right, yeah, it's not 9 to 10, yeah, sorry. It's too early in the morning to actually take a, good, I was already a little bit upset. Thank you, good. Right, since I want to say a few things about the fundamental case, since the solvability, whoops. If you have square free D, then the solvability of negative Pell, that is just to say that the fundamental unit in Q square root D has norm minus 1. For those of you who worry about the difference between the ring of integers and the ring Z square root D, for the unit groups, there's never an issue since the index is 1 or 3, and if you take a cube, the sign doesn't change anyway, so this is the same thing. And the fundamental unit, that is something that its norm determines whether the group that Gauss looked at, which is the narrow class group of that field, narrow class group, of Q square root D, is in fact the ordinary class group. And narrow means that you mod out by ideals having a generator of positive norm, which is not the same definition as ordinary class group where you don't care about the norm. If you have a fundamental unit to change the sign of the norm, there is no difference. And if the norm is plus 1, there is a difference. Namely, then there is an element of order 2 that you have to mod out to get from the narrow class group to the ordinary class group. And that element, which is called the Frobenius at infinity, so this is about a Frobenius distribution, that's the ideal class of square root D, which is obviously a principal ideal, but its generator has norm minus D, negative. Whether you can change it to plus D using this fundamental unit is exactly that question. And this is the 0 element in the group CD. And that's the way you attack the problem. You use class group theory and you look at the corresponding fields, and that's the beginning of a long story. And the one-line summary of the conjecture, at least, how it arises, is that this Frobenius at infinity, it lives in the two-torsion subgroup. And the two-torsion subgroup, that's the group of ambiguous ideal classes that Gauss defined, has a well-known order. It has order 2 to the t minus 1, where t is the number of distinct prime factors of D. That's called, if you want, also genus theory. So you might think that this Frobenius is a random element in this group of which you know the order. But that's not the case in practice, and the reason is that this Frobenius at infinity is also contained in twice the class group. And that is called genus theory, since twice the class group, if you mod out by twice, you get the genus group corresponding to the genus field of this real quadratic field, and that's the thing that you get by adjoining the square roots of the primes, dividing it with an appropriate sign, essentially. And this group, so that's an elementary abelian 2 group, so it looks like z, not 2z to a certain power, that I will call R4, and this R4 is the 4 rank of the class group. R4, 4 rank of CD. And there's a whole theory on 4 ranks for quadratic class groups, which is due to Redi, so his work goes essentially into this conjecture, and its distribution is also well known if you fix the number of prime factors. And if you think about it for a while, how random this Frobenius at infinity should be, then the principle that gives rise to the conjecture is that f infinity is 0 with probability 1 over 2 to the R4 plus 1 minus 1. So for instance, if the 4 rank is 0, then the genus field is in fact the narrow 2 Hilbert class field, which is real. Then you know that in fact the answer is going to be yes, it is solvable. That's the case where it is 1 over 2 minus 1. But already for 4 rank 1, we don't know how to prove this principle. So just to, if D is P times Q, maybe we should call that small d, where P and Q are congruent to 1 modulo 4, that's also something that was already studied by Dirichlet, then if the Legendre symbol is equal to minus 1, then the genus field does give you the 2 part of the class group. Then this 4 rank is going to be 0, and then D is in fact in sigma minus. And if the Legendre symbol is plus 1, you have to work harder. And there are results, this is all Dirichlet. For instance, if you can look at the Archimedean character of the 4 Hilbert class field, and that is determined by biquadratic symbols. So whether things, and it's this quantity that determines. So if you make it complex, then you know that D is not going to be. These are criteria. So you see that you already get densities, at least 1/2 of the D's of this form, you know the answer. It's in minus, so it's already 50%. It's not going to be everything, since this condition sort of cuts it off. So it's going to be between 1/2 and 3/4. And the density that you should have, according to the philosophy, is that it should be 2/3. But that's completely open. So even though this has been the conjecture, the theorem has now been proved, which is an asymptotic statement, at finite levels, already these basic things, people don't know what the answer is. This should be the density if you look at these D's of this form. And we know it's between 1/2 and 3/4, but not much more than that. Well, something more maybe in the meantime, but still not the limit. So already here there are still many open questions. I'm not going to say more on the heuristics. So there's an asymptotic statement. It went sort of in a different way. So fixing the number of primes, which was supposedly the easy case, and the conjecture was obtained by letting this number tend to infinity, which it does so slowly, like log x, so you don't see it in practice. It also explains that if you do it numerically, look at this p, you don't find it at all. If you just take x equal to 10 to the 4, you get something like 86%. And at 10 to the 7, it gets below 80, not anywhere close to 58. And the reason is that if the number of primes is still small, for instance, if D itself is prime, 1 mod 4, then you know the answer. It's 100%. And that sort of spoils the density in the beginning. And only when you're very far out, you're going to see it. But you're never going to get there. So you have to test these conjectures in different ways, not by just using your computer and compute that for big values of x. You're never going to be anywhere close to 58%. Okay, so there's still many things to do. We're also at finite levels, and I think that I will spend the last 50 minutes or so on the non-fundamental case. So what does that take? And maybe by way of introduction, I'd like to discuss another old problem. The reason being that we're talking about the Frobenius at infinity in the group that is CD, which is the narrow class group of Q square root D, the fundamental discriminant. And that has an order, let me call it OD, ring of integers. In which the Pell equation may or may not be solvable. We know how probable it is, that's the P. But now we are looking at the order of index F, O F squared D. And the question is, in here there's this fundamental unit, epsilon D, which may have norm -1, but in here, that needn't be fundamental. That needn't lie in the order of index F. So here we have a different fundamental unit, F squared D, of which you want to know its norm. And that will be a power, and the question will of course be, will it be an even power or an odd power? Since if this has norm -1, and this is an odd power, then you also have norm -1. That's if and only if. So it's about the order of a unit, a fundamental unit, in this case, modulo f, that you need to study. And the basic example that people typically think of in this context, another old question that I may remind you of, because it's also still completely open, it's the question of Eisenstein. It's in a paper from 1844, which has a vague title, some questions on whatever, quadratic forms or, yeah. And the question that he phrases there is in the case where your quadratic field, so it's real quadratic, and the prime over the prime 2 is inert, so you're dealing with d's that are 5 mod 8. Then you know that the ring of integers, d is 1 mod 4, is z 1 plus square root d over 2, and the ring that people always look at for Pell is z square root d, which has index 2. And the question that Eisenstein asks in modern terminology, he talks about binary quadratic forms and the class group. And the question comes down to this fundamental unit, which lies in this ring. How often will it actually lie in z square root d? So his way of phrasing that is, if you look at the Pell equation, if you write it like this to allow for these numerators 1/2, can you solve it in odd integers? Solvable in odd x and y, or in other words, will the fundamental unit be here or will it lie there? And this is just asking for the residue class of the fundamental unit in the ring if you take it modulo 2. And of course, it's going to be a unit. And if I say the fundamental unit, you should say, well, that's only up to sign, and you can take its inverse. So it's not exactly unique. But if you go modulo 2, the sign doesn't really matter. And if you take, this is a group of order 3. So the question is just whether it's the trivial element in here or not. And if the residue class is here the trivial element, that means exactly that your fundamental unit lies in the order. And in that case, as Eisenstein remarks, the class number of the order of index 2 is 3 times the class number of the maximal order. So there's 3 times more binary quadratic forms. That's what he's excited about. And how often does that happen? And clearly, if you phrase it like this, and the question is whether this unit is going to be trivial in this group of order 3 or not, then the obvious choice is, or the obvious guess is, that this happens with probability 1/3. And Hugh Williams has done calculations more than 20 years ago, but there were certainly computers in those days, and in practice that's exactly what happens. So it appears to be 1/3, but we cannot really prove it. There are partial results that I also proved long ago. You can, of course, relate this 3 in the class number to Davenport-Heilbronn results. Yeah, there cannot be, you can count cubic fields, and in that way you can show that the density, which is supposedly 1/3, it is certainly no more than 1/2. That's the theorem. But a lower bound, which is positive, or is already impossible. It's an infinite collection, but lower density, which is positive, we cannot show. But it does show that fundamental units, if you take them modulo your favorite conductor, they have a tendency to be equidistributed. And that's exactly what underlies the second half of the conjecture, or the question of Nagel. What do you need to do to get the non-fundamental case? And why does it give this funny expression? And that's what I want to explain now. This is this one. So as I said, the bit that you want to determine is the order of the fundamental unit, essentially modulo f. Another thing which is very German, and not everywhere in France, is the way we clean the blackboard here. It's very clean. and I don't think it takes more time than the normal eraser. So if you're an organizer here, most of the time you spend is cleaning blackboards between talks. Which is, of course, not an unpleasant thing to do. So, as I said, so how do you find this conjecture? And then, of course, you still have to prove it. That's another detail. As I said, if you have a D which is in square free and negative PEL is solvable, so I encoded this by saying it's in sigma minus. I don't know whether sigma is still there somewhere. Maybe. No. There is sigma minus. So S is all D's which is solvable, and sigma minus is the square free ones. Then you can wonder, and it's certainly not in general true, that if you take the fundamental unit in the order of index f, then it's also going to be in sigma minus. Clearly, this is always true if the order of index f has a fundamental unit of norm minus 1, it's going to be an odd power of that one, and that also has norm minus 1. But as I said, this is not in general true, because this order is, if you write this as epsilon d to the k, then we're just interested in the parity of k. So what is k? Well, k is the order of this element epsilon d. If you take its residue class, well, you just need to look mod f. Yeah, you take epsilon d, and to check whether it's in the order of index f, you go mod f. So you look at it in O mod fo star, OD FOD star. And it lands in the order of index f if the image lies in Z mod fz star. The reason being that this order, if you write it as Z plus Z omega d, then this order is Z plus Z times f omega d. So you have to look on the on the second component to see whether it's divisible by f. And this order, that's the question. Is it going to be even or odd? That will determine whether the implication is valid. And if you look at this, you get a few things that are obvious. First of all, if you use the Chinese remainder theorem, you see that, it's your basic lemma. You take your D in S minus, and to conclude that F times D is also in S minus, the order has to be odd on all the components at the various primes. So you see it's enough, this happens, F squared D is what I'm trying to do. That's if and only if P squared D is in S minus for all P dividing F. So you can decide prime-wise whether this is the case. And it depends a bit on the P that you're looking at, dividing F, how it behaves in this order. First of all, if you see that if you take P equal to 2 or a prime 3 mod 4, then already by congruence conditions that we had from the beginning, you see that you're not in, so P is 2 or P congruent 3 mod 4, then obviously P square D is not in S, not in S minus because it's not in S. That's the definition of S, right? There are no primes 3 mod 4 dividing it. So these primes you can sort of throw away immediately. You're only dealing with primes that are going to be 1 mod 4. And they come in 2 versions, in 3 versions actually, depending on the Legendre symbol. So if it's 0, 1, or minus 1. And in each of the 3 cases, there's something to be said. Namely, if P divides D, then if you look at this group, you take F equal to P, which is then the square of an ideal, and you mod out by Z mod PZ star, you get a group of order P. So obviously the order of anything in that group is going to be odd. So if P divides D and you take your D in sigma minus, then P squared D is also in sigma minus. Sorry? Sigma. Sorry, what? P, yeah, excuse me, 1 mod 4 is certainly to be added. So 3 mod 4, yeah, so now we take 1 mod 4, yes. We're only dealing with primes 1 mod 4. And your question was what?
S or sigma, I mean, sigma means...
Yes, you are completely right. Now it's no longer square free. So if negative PEL is solvable for D, and you replace D by P squared D, just asking whether you can have Y divisible by P in the solution to negative PEL, the answer is yes, you can do that.
So what would you do for B and S?
Where, sorry?
In part 1 of the lemma, you have a sigma that should be in S.
Yeah, thank you, sorry. Yeah, all these letters, so S. It's no longer squared, definitely. Good. So, we're now looking at primes 1 mod 4. Of course, the primes 1 mod 4 are going to give rise to this funny expression, right? You should think of psi p for the probability that given that you have a d in sigma minus, that you, yeah, so if you take d equal to p, which then needs to be congruent to 1 mod 4, or maybe not 1 mod 4. If you take d equal to p, this holds with probability, and of course it's going to have a meaning, probability psi of p. Yeah, you want to have a fraction of d's for which...
You mean F equals?
Yes, sorry.
Where you were at P equals P on the left.
Yeah, sorry, this is with f. Let me phrase it for p, sorry. Yes. Oh, yeah. Okay, so the notation needs to be repaired a little bit. It's about, maybe I should have used the solvability of negative PEL all the time. So the question is, if it's solvable for D, is it solvable for F squared D? You're going to decide that prime-wise, and for a prime, you want to find this expression, how likely it is that epsilon D essentially is in the right residue class modulo P. Sorry for the mess. Yeah? It has nothing to do. It has F equal P. That's what I tried to say. Sorry. So, and F is now gone, so it's just P. Okay. So this is the statement which is still very vague. So the way we're going to define this psi of F, so maybe, if you do it, maybe I should phrase it like this, F psi of F. And this statement gives rise to the fact that psi of F can be defined as the product of P dividing F psi of P. That is step 1. Yeah, you can just, that's the Chinese remainder part, you can just do it prime-wise. And secondly, psi of 2 is 0, and so is psi p if p is congruent to 3 mod 4. This psi will be a multiplicative function. That's the reason why you get this Euler type product. And the only thing that you need to compute now is psi of p if p is 1 mod 4. So, and as I said, we're going to have 3 cases, 0, -1, or for the Legendre symbol. And so maybe I should phrase it, should start here, p congruent to 1 mod 4, sorry for the mess. If the Legendre symbol is 0, then a fundamental unit of norm -1 in the maximal order will also be norm -1 in the order of index p. If the Legendre symbol is -1, the same thing holds. P squared D is also in S minus. And why is that? In that case, this group, so if D over P is -1, then you're just looking at Fp square star that you mod out by Fp star. And you wonder what the residue class of epsilon D is going to be in there. But from the fact that the norm is -1, you know that P plus 1 is actually going to be -1 in Fp star. Since the norm is just Pth powering And minus 1 is a square modulo p, because p is 1 mod 4. So that means that if you take its square root, you're still in fp. And p being 1 mod 4, you see that this is an odd power, which is in fp star. So the order is definitely going to be odd. So inert primes are also easy. And the difficult ones are the primes that split. And in that case, the statement becomes something slightly different. There's actually a criterion, which is not just yes or no. Oh yes, well, this is to be remembered maybe, but I need the space now. Then you have p squared d in s minus, if and only if the order of epsilon d in O mod PO star, OD mod POD star, maybe we should say, is congruent to 4 mod 8. In view of time, I won't really go into this. It's not very complicated. You should look at this algebra, which is then a split algebra, fp star times fp star modulo fp star embedded along the diagonal. That's of course isomorphic to fp star. If you map elements of the form xx prime to the quotient, and you discover that you're looking under that map to the residue class of minus the square, which has to be odd, and this is what comes out at the end. So it's just about the two-part, and of course the order, the two-adic behavior of the order in that group. That's exactly what gives rise to this order. Since how do you complete the argument in minus 1 minute? You assume, that's the base of the heuristics, that the fundamental unit, if you take it mod f, is going to be randomly distributed, equidistributed. And of course that means if you take it up to sign and inversion, you have to ask the right things. And that equidistribution, you then couple it with the observations here. So you need to know, if you take elements of S, and you take them modulo f, it's not, there's equidistribution by definition modulo f, but not if you just take these sums of co-prime squares. So the distribution is something that was looked at by Rieger in the 60s, and the zero class is sort of gets more than the equal share if you look at S's of this form. It's something completely explicit, and for every residue class, you then look what you need to do. And residue classes that are zero, so you split it out. Yeah, this is in fact, you can take f, just the product of primes 1 mod 4, and map to the product of the associated z mod pz's, p dividing f, which are all going to be 1 mod 4. Yeah, so f, the interesting f's for which psi doesn't vanish are just products of primes 1 mod 4. And you look at this map and which residue class they are. And they come with a weight according to Rieger, and then if you have the zero class, you're happy. If you have the inert class, you're also happy. And if you hit the split class, you have to take into account how likely this is. And an element in a cyclic group of order p minus 1 having order 4 mod 8, if you look how many classes there are, what comes out is 2 to the 1 minus the order of 2 in p minus 1. So if p is just 5 mod 8, for instance, only 4 dividing p minus 1, it has to be 1 mod 4, then you see that you're dealing with half. You actually need the non-squares have order 4 mod 8. Yeah, they have maximal 2-power order in fp star. And in general, this is what you get. And if you then do the administration, add it up, is the value that you get is here. So the reason that you get this quantity is just the sum psi f over f squared. F is 1 up to infinity. So you take all the orders, you sort them by f, and for given f, you see how likely it is that your fundamental unit has odd order. And that's multiplicative, and the p's 1 mod 4 are the only ones that actually come into account in the stats we're dealing with here. And my time is up, so I need to stop here. Thank you.
in person this week.
We have a special coffee break.
Interrupt you even if you went over time.
Well, the coffee break is in 1 minute.
It's fine.
So-
I mean, well, we said it, right? But he's the chef Morlet, so we said.
Then you can take 4 minutes extra, right? Without being punished by the chair.
So is there any question for Peter? Please.
Yeah.
Can you say just something briefly about this probability, like where that the Frobenius infinity is 0, probability 1 over 2 to the r4 plus 1 minus 1, where that denominator comes from?
Yeah, I can certainly do that. So you have the theorem of Gauss on ambiguous ideal classes, which tells you that the 2 part is just generated by the ramifying primes with one relation, right? So you have f2 to the t that maps surjectively with a certain kernel to this 2 torsion. And your question is, in our case, is this kernel actually the Frobenius at infinity? That's what you want to happen. Yeah, so this is if you send the ith basis vector to the ith plus of the ith prime, right? So this is the map that sends ei to the class of the ramified primes. Yeah, so your D is a product of pi's, and these ramifying primes are squares of Gothic p's, right? So these are the generators of the 2 torsion subgroup of the class group, and there's T of them, and they have one relation. And the question is this the relation? That's negative Pell. And Redi tells you how this group embeds in C mod 2C. That is the Redi map with the Redi matrix. It's essentially the genre symbols. And you know, since for our D's the genus field is totally real, that F infinity is at least in the kernel of this map. So you view this map, that is in fact how you typically define the Redi map. You don't know relation, you define it here. And you know that F infinity is in the kernel of the Redi map R4. And that's a subspace of dimension 4 rank plus 1. It's a non-zero element in that subspace. And the question is that the kernel? So that gives you that's the heuristic.
Is there any other questions? Yeah, sorry. Actually, this talk is been recording, so we need to use the microphone to ask the question. So sorry.
You have your permission written
Yes.
3 times.
Is there a natural function field analog of this conjecture?
Well, I think people actually do talk about real and complex quadratic fields also in the function field setting. I never looked at it, I must say. It feels certainly less natural, but of course you can, all these questions, you can phrase your favorite analog. I mean, negative Pell is just about the Frobenius being something. Of course, the obvious conjecture is if you, it's not just being the trivial with that, it should be equidistributed over the kernel, for instance. That is what you expect. That is also the case. So that is not what you need for negative Pell. Yeah, typically what you expect is that Frobenius elements in a certain context are equidistributed over some Galois group or vector space, and sometimes in Sato-Tate it's traces. You have to look at it. That's sort of the bare setting. So whatever conjecture you want to come up with, there's lots of space. But as far as I know, there's no direct analog that people say this is negative Pell for function fields.
More questions? Comments? I was very strict with the time, but it's fine. We have the coffee break now, so there is time. If you want to ask.
27 minutes of coffee break. Sorry for the 3 minutes. Oh yeah, they will look. It will stare at you. Be careful.
I'm thinking about it like an analogous question, but not just for quadratic fields. Let's say I have like a norm equation over a rank 1 unit field. Let's say like a complex cubic field, and I would like to see which ones have norm -1, the fundamental unit, and then you would generalize.
Well, in cubic fields, -1 is already is a cube, right?
Yeah.
So.
Not a specific example for the cubic field, but let's say like a rank 1 thing, right? And you want to see which ones, when can you have sort of the analog of the negative Pell equation, so it will be the negative norm equation. So you will have to define you set S specifically, so you could say like take monogenic number fields, so you can do the things. So is there sort of people who have studied these in a similar way? Because
Well, as I said, the sign of the norm is not an issue here because the fundamental unit minus the unit has minus the norm. So it's not the sign, but the behavior of the unit on average typically, if you take it modulo your favorite prime, if that makes sense, you expect it to be equidistributed over families of cubic fields.
Okay, so
That's not exactly what you're asking,
yeah,
but
I mean, I just put just the cubic field to have rank one thing in
Mhm.
like something that had the unit whatever thing rank
they have a
one.
fundamental unit. That's what
Yeah,
you say,
exactly,
which
yeah,
is
so you have-
unique up to silent inversion, more or
Exactly.
less.
So
I mean.
because you would do very similar things, right?
Yeah.
It only depends on the equation looks well. The norm equation, you could just work it out specifically.
Sure. What do you want to ask?
I would like could you do the same sort of behavior, so the same sort of study if you have sort of the quadratic? It wouldn't be a quadratic equation. It would be a norm equation.
Sure, but you have to have something else about a norm, not just the sign of the norm. That's ill-defined here because you can make it whatever you want. But other things of the norm, of course, you can ask. Congruous conditions that are not the sign condition.
Exactly. So it's, okay.
Yeah, well, given that the quadratic case is still somewhat complicated, the conjectures are not that difficult to formulate typically. Yeah, you look at it in practice, it appears random, you say, oh, that should be random. But proving this already in the quadratic case is open for this negative PEL for the orders already. So I don't expect it to be easier in the cubic case.
More questions, comments? We can also discuss in the break. So many people gave you more conjectures and ways of generalize, but no hints about how to prove your conjecture.
Yeah, well,
Maybe for another occasion.
for the next 30 years.
Let's thank Peter again.
Okay.